So this, I think everyone is clear with this concept. We started this yesterday, that is sigma 11 was equal to C11 epsilon 11 dot. Likewise, C12 epsilon 22 dot plus C13 epsilon 33 dot. And we understood that this C12 was equal to C13, and we assigned this another constant A, while C11 was termed as B. So we got sigma 11 as B epsilon 11 dot plus A. A can come out now common. So this was E22 dot plus E33 dot. And we made a mathematical manipulation. What was the mathematical manipulation? We added and subtracted A epsilon 11 dot. So if you add and subtract this, what do you get sigma 11 as? Finally, B minus A epsilon 11 dot plus A common epsilon 11 dot plus epsilon 22 dot plus epsilon 33 dot. Now what is this, if you remember from your solid structures course? This is sum of what? Sum of, this is sum of what?
Strains.
Hanji? This is sum of strain rates. Strain rates. And this is called as volumetric strain rate. As you had volumetric strain in case of solids, in case of fluids, you have a corresponding volumetric strain rate. And that is represented by this delta dot. So with this manipulation, what do I get sigma 11 as? Finally, sigma 11 is equal to, I can mark this as another constant and this as another constant. Now please be careful what I am putting here. This is 2 mu and this is lambda. So I get 2 mu E11 dot plus lambda delta dot. And you will get to know why I have put 2 here. This is just a mathematical manipulation. I am writing down B minus A with another constant, that is 2 mu. And what is mu? Mu is your dynamic viscosity or first coefficient of viscosity. Likewise, lambda is called the second coefficient of viscosity. Nothing more than that. So I have got sigma 11 written down as 2 mu E11 plus lambda delta dot. So this is sigma 11 is equal to 2 mu E11 dot plus lambda delta dot. Likewise, sigma 22 will be equal to what? Sigma 22. Akash. Sigma 22.
फिर कोई और आ जाएगा 2 mu ही आए 2 mu E double 2
plus
beta.
Why beta?
नहीं सर लैम्डा अगर A के लिए था तो वैसे वो चेंज होता रहेगा ना सिग्मा 2 के लिए भी.
चेंज क्यों होगा बताइए.
एक मिनट पहले क्या था A था हमारा.
C12 is equal to C13, ये तो क्लियर है.
यस सर. अच्छा हाँ यस सर. यस
ठीक है. And you know that C21 is equal to
C23.
C23. So C12 and C13 both are equal to say A, and C21 and C23 are equal to B. Then is A equal to B or not?
Yes sir.
Because it is isotropic.
Yes sir, because it is isotropic.
So that's why we don't have lambda 1, lambda 2 or mu 1, mu 2. We have single values of these coefficients. Likewise, sigma 33 is equal to 2 mu E33 dot plus lambda delta dot. So this is the final equation in which what have you done is you could represent stress in terms of strain rates, and you require how many constants now? Only two independent constants. Is that clear?
Yes, sir.
You require now only two independent constants. Now it is solvable. So the entire process actually was unsolvable till our assumption was that it is anisotropic. Because in anisotropic, we started with 81 constants and 9 equations. We simplified it to 36 constant and 6 equations. And finally, 9 constants and 3 equations. But in all these cases, that is the case of anisotropic case, we were having number of unknowns far more than the number of equations from which it is to be solved. So it was only when we gave the assumption of anisotropic, or we made this relaxation, we could actually end up in a more solvable equation. So this is now equation in terms of two independent constants, that is mu and lambda. Is that clear? And what are sigma 11, sigma 22 and sigma 33? These are principal viscous stresses. And I could equivalently write down in terms of rectangular components also. So this is in terms of principal components. So please be careful now. How many of you are clear with this? This is what? Total state of stress written down in terms of
shear stress.
Written down in terms of what? This is not shear. This is what? This is total state of stress at a point, which includes what? Pressure
force components and viscous force components.
And viscous force components. And please remember, tau does not designate shear. I have already clarified this in previous lectures. I could use sigma or tau alternatively. What will dictate that whether it is tensile or shear is the index.
Yes, sir.
If it is the same index as it is in this case, this is representing normal. And all others are zero. It means these are principal.
Yes, sir.
So what we have done is we have just actually simplified the stress terms in the viscous matrix to this format. Nothing more than that. So we have been able to convert stress into more measurable quantities, that is strain rates. And that was our agenda, to convert stresses to more measurable quantities, that is derivatives of velocity vectors. So what is E11 dot? What is E11 dot? Curly U by curly X. What is E11 dot plus E22 dot plus E33 dot? If you remember, what is this? Curly U by curly X plus curly V by curly Y plus curly W by
curly Z.
Curly Z. Now, if you remember the continuity equation, what was continuity equation? Curly rho by curly T plus what was the continuity equation?
V into delta
V.
This was the continuity equation. If I assume
yes, sir,
rho is a constant.
Yes, sir.
If rho is a constant, then what I am left with? this term goes to 0. This is 0. This is a constant. It means this term is equal to 0. So what does that tell you? Delta dot is equal to 0 in case of incompressible fluids. And that is clear from your common sense also. That is, the fluid element will not change its volume if it is incompressible. That is as simple as that. So volumetric strain rate is equal to 0 for incompressible fluids. Is that clear?
राइट में आपने डेल लिखा है, वो डेल भी नहीं।
हाँ जी,
राइट साइड में आपने डेल लिखा है, वो डेल भी नहीं होगा।
कौन सा, ये वाला? दिस इज डेल्टा डॉट।
अच्छा,
दिस इज डेल्टा डॉट। आप, मेरे को लग रहा है कंफ्यूज कर रहे हैं ये वाली चीज। आई एम, सो यू आर, आई थिंक, कंफ्यूजिंग दिस विद, वेट फॉर अ सेकेंड। ये कॉन्टिन्यूटी इक्वेशन में क्या होता है? डेल डॉट ये होता है, शायद आपको याद हो।
जी सर।
ठीक है ना? लेकिन मैं, और ये क्या चीज होती है? व्हाट इज दिस?
0।
हाँ, अगर ये स्टेडी स्टेट है और रो कांस्टेंट है तो आप इस चीज को ऐसे कर देते हो।
हाँ सर, कर दें। यस सर।
that is equal to 0 and you know that rho is a constant, so what is 0?
Del
This
U.
is 0. And what is this actually? Delta dot. That is this volumetric strain rate. That is E11 dot plus E22 dot plus E33 dot. And E11 is this term, E22 is this term, and E33 dot is this term. Is that clear now?
Yes sir.
Clear है आपको?
Yes sir.
So this was in terms of principal stresses. Now if you want to write down in terms of, तो ये किसी को इक्वेशन अगर डाउट है प्लीज आस्क मी. So what does these equations represent? What are tau 11, tau 22 and tau 33? What are these
total
values?
stresses. Total stresses.
Total principal
Stresses.
What are these terms?
The pressure force components.
Pressure forces. And what are these components?
Viscous forces.
Viscous forces. Clear hai? Now if you want to write down in terms of rectangular components means, now instead of principal stresses I am representing in general terms. That is, if I want to write down tau xx, then this will be equal to what? Pt delta ij plus 2 mu E xx plus lambda delta ij. If I want to represent tau xy, what is tau xy? What is tau xy? Tau xy is the total shear stress at that point.
Yes, sir.
So now let me know whether shear stress will involve these terms or not.
वो क्या लिखा हुआ है डेल्टा के आगे?
कौन सा वाला?
ये डेल्टा 0 रहता है ना इसमें?
इनटू डेल्टा ऐसा ही.
हाँ, ये क्या चीज है? ये डेल्टा आई जे क्या चीज है? दिस इज कनॉकर डेल्टा. इसकी वैल्यू क्या होती है? 0 when
I not equals to j
and is equal to 1 when I is equal to j. So you are actually representing with this single equation. This is a very powerful equation. Try to see. If I is equal to j, then delta ij will be 1. That is, whenever you say tau xx, tau yy, tau zz, this will be equal to what? Help me write down this. Minus pt, or so, what will be this? Minus pt.
pt.
यहाँ पे माइनस आना चाहिए था. माइनस pt प्लस 2 mu
E XX
plus lambda delta dot. Likewise, tau yy minus pt plus 2 mu E dot yy plus lambda delta dot. And EZZ minus pt plus 2 mu EZZ dot plus lambda delta. Now, what about shear stress components? What do you know? Delta Ij, say tau xy will be equal to what?
2 mu
2
E XY
mu
dot.
E dot xy. What has happened to these terms? This was 0 and this is also 0 when I is not equal to j. So that's why in case of shear stresses, you only get this expression. Is that clear? So this is the entire matrix now in terms of rectangular components, and you can remember this matrix by this single equation. That is the power of this notation. This single equation, if you remember, you can actually remember this entire matrix. And any doubts to anyone, please ask if you have any doubts in this. So as a global view, what we have done is we have simply converted the stress terms into strain rate terms in the viscous term of this equation. This was already there in case of Euler equation. This was in terms of stresses. The entire process was to convert the stress into the corresponding strain rates. And clear hai? Any doubts to anyone? So I am summarizing here for you. This was the Cauchy-Navier equation. Cauchy-Navier equation, how it is different from Euler equation? Which terms are additional here? This is Cauchy-Navier equation. If I ask you what is the Euler equation, which terms will you not include?
3 terms लिखे हैं सर साथ में.
ये. These
Yes,
are
sir.
not there in Euler equation. So this has popped up in Cauchy-Navier equation because we are treating viscid region of flow or any region of flow. Now from Cauchy-Navier to Navier-Stokes, what we have done? From Cauchy-Navier to Navier-Stokes, what we have done? We have converted these stress terms into what? The corresponding strain rates. So that is the essence of Navier-Stokes equation. So you start with conservation of linear momentum. You include pressure forces and viscous forces as surface forces. And body force has all the components in X, Y, and Z directions. And if you don't convert stresses to more measurable quantities, then it is called Cauchy-Navier equation. But if you put efforts to convert stress terms to corresponding strain rate terms, that equation is called the well-known Navier-Stokes equation.
वो नीचे करना थोड़ा सा.
हाँ, एक second. If you have any doubts, please come up with your doubts. Wait for a second. So this is the Navier-Stokes equation. Not the Navier-Stokes equation, but Navier-Stokes equation will come afterwards. But this is what we have done. We have converted the stress into strain rates. Now if I substitute this in this equation, you get the Navier-Stokes equation. Is that clear? So these terms, if I substitute with corresponding strain rate terms, this Cauchy-Navier equation will turn to Navier-Stokes equation. हाँ जी, क्लियर है? Any doubts to anyone? I will take one component here so that things are clear to you, and rest will follow in Y and Z components you can derive yourself. So I am deriving for X component. It is not a derivation, but just substituting the value of sigma xx, sigma yx, and sigma zx. Nothing more than that. So this is what, which is this equation, if you remember, which is this equation? Cauchy-Navier equation. What substitution do I need to make? This substitution. What is sigma xx, if you remember? What is sigma xx? What is sigma xx?
Normal normal
What should I substitute? What is sigma xx? Try to think.
For the principal stress.
Not the principal stress. Please.
Sir, PT plus 2 mu
देखिए, tau xx is minus PT plus mu E
XX
plus lambda delta dot.
delta
And
dot.
what is this?
viscous
Sigma
force
xx.
component.
This is sigma
Yes, sir.
xx. You remember?
Yes, sir. Yes, sir. Yes, sir.
So what is sigma xx? Simply 2 mu E dot
Ex.
xx plus lambda delta dot. And what is Ex? E dot xx? Curly U by curly x. What is delta dot?
0.
Delta dot. In case of general, it is
du by dx plus
curly U by curly y
curly
plus.
u by curly v by curly y plus curly w by curly z.
Is that clear?
Yes,
So
sir.
what you have done is you have substituted here. So this is curly by curly x. So I am showing this term. So sigma xx is 2 mu curly u by curly x. This is this term plus lambda into delta dot. Is that clear? Is that clear or not? Is that clear
Yes, sir.
or not?
Yes, sir.
Yes, sir.
बिल्कुल.
ठीक है? And likewise, I can have for sigma yx and sigma zx. Sigma yx and sigma zx. So what is sigma
एक ही
yx?
टर्म रहेगा सिर्फ 2
What is
mu e
tau, sorry, tau yx किसके बराबर होता है?
2 mu e dot xy.
इसमें pt वाली टर्म तो नहीं होगी?
No, sir. वो zero होगी उसमें.
Zero होगी, तो इसमें क्या होगा? 2 mu
E xy
dot
xy
yx.
yx. Yes, sir.
Yx only. And what is E dot yx, if you remember?
Del u by del x plus del v by del y. Half of.
Curly v by curly x plus
Yeah, curly v.
curly u by curly.
Curly y.
So this half will cancel out with this 2. And
Yes,
what you get? Mu into curly v by curly x plus. Is that clear? Any
yes.
doubts to anyone? Likewise, you can have for sigma zx this term. Is that clear?
Yes.
So in Cauchy-Navier equation, I am actually making substitution on the left hand side part just for the viscous terms, nothing more than that. I am not touching upon this right hand side. So after manipulation, certain mathematical manipulations that I will not cover here, these are just mathematical manipulations that you can also try at home. We get this as
slide
the final equation in x direction. This is the
Sir, आप ये
final
slides दे दोगे तो
Navier-Stokes
आप लिखोगे
equation in
फिर।
x direction. And these terms have
Hello,
been
sir.
given special names. This is called the pressure gradient term. This is called the volumetric dilation term. What do you mean volumetric dilation term?
वॉल्यूम के रिस्पेक्ट में जो चेंज आएगा उसके कॉरेस्पॉन्डिंग जो टर्म
So
होगी
please remember delta dot is equal to curly u by curly x plus curly v by curly y plus curly w by curly z. This is also equal to delta del dot v. Please remember this formula. So that's why you see a delta dot v here instead of delta dot, because this is much more popular. Divergence of velocity field. What is divergence of velocity field? This will be again same thing only. So instead of delta dot, you will see in the textbooks del dot v. This is just a more popular notation, nothing more than that. Instead of delta dot, they are writing down divergence of velocity field.
सर ये म्यू प्लस लैम्डा कहाँ से आया फिर इसमें?
म्यू प्लस लेमडा कहाँ से आया?
अच्छा वो ठीक है ठीक है ठीक है,
वो क्या
ये
होगा?
समझ गया।
मैनिपुलेशन करके ना, जैसे ये आप देखो यहाँ पे जो हम इक्वेशन लिख रहे थे उसके अंदर ये देखो, यहाँ लेमडा करली यू बाय करली एक्स के साथ लेमडा भी था और म्यू भी था। तो इनको सॉल्व करके, मतलब बेसिकली टर्म्स को ऐड वगैरह करके यू गेट दिस फाइनल इक्वेशन।
ठीक है,
क्लियर है? और इसको और सिंप्लीफाई कैसे कर सकते हो? अगर म्यू कांस्टेंट है तो क्या हो जाएगा? इफ म्यू इज अ कांस्टेंट, व्हाट डज दैट?
कॉमन आ जाएगा।
कॉमन आ जाएगा। सो व्हाट डज दैट गेट यू? करली यू, सॉरी म्यू करली स्क्वायर यू बाय करली एक्स स्क्वायर प्लस करली स्क्वायर यू बाय करली वाई स्क्वायर प्लस करली स्क्वायर यू बाय करली जेड स्क्वायर।
सर इनकम्प्रेसिबल के लिए फिर ये टर्म जीरो जाएगा।
कौन सी टर्म? ये वाली टर्म।
डेल्टा।
अगर इनकम्प्रेसिबल है तो ये टर्म जीरो हो जाएगी। अगर प्रेशर वेरिएशन नहीं है तो ये टर्म जीरो हो जाएगी। अगर ये नहीं है, बॉडी फोर्स नहीं है, तो ये टर्म जीरो हो जाएगी। इट इज एज सिंपल एज दैट। इज दैट क्लियर? सो आई एम राइटिंग डाउन हियर equation for x momentum. So this is minus curly pt by curly x plus curly by curly x. So this is the way to remember it. You also can follow this. Del dot v plus
mu into del square u by del 2u by del x square plus del 2u by del y square.
this is the case plus rho bx. This is equal to what?
Zero. नहीं, rho
Curly
sir,
rho u
total
by
derivative.
curly t plus del dot u rho b. This is the x momentum Navier, or you can say this is the Navier-Stokes equation in x direction. Now I want from your side the corresponding y and z component. What should I do? Quickly follow the symmetry. It is very easy to remember this equation, because if you remember this equation, just putting other terms equal to zero is the entire fluid mechanics.
Sir, rho into
Minus curly pt by curly
y
plus
plus
curly by
del y
lambda plus mu
delta into v.
Delta dot v. So I should put it like this. It is more appropriate to put in brackets here. Plus mu. Now be careful. What should I put?
Del v square. Del 2v.
Curly square v by curly x square plus curly square v by curly y square plus curly square v by curly z square. Plus rho by is equal to curly rho v by
rho into
curly t
substantial derivative of v.
V rho capital V. Likewise in the z direction. Is that clear? So please remember, as far as laminar flows are concerned, laminar flows for Newtonian fluids, and that is the most popular thing in your engineering. Laminar flows in case of Newtonian fluids, Navier-Stokes equation is the ultimate equation. All other equations, whether Couette equation, Poiseuille equation, Euler equation, any equation you name, is actually a special case of Navier-Stokes equation. So that is the power of Navier-Stokes equation. And you will get to know why do we require other equations. Now, if Navier-Stokes equation is the ultimate equation,
सेकंड ऑर्डर नॉन लीनियर इक्वेशन सही है.
so we don't require Couette equation, neither require we Darcy equation, Poiseuille equation. These equations are just approximations of Navier-Stokes equation. Because if Navier-Stokes equation was solvable for all geometries and boundary conditions, then we wouldn't have required this. We wouldn't have required this if Navier-Stokes equation would have been solvable for all geometries. And is that clear?
Yes.
I'm giving you one example, very small example, and that will actually broaden your perspective regarding Navier-Stokes equation. So Navier-Stokes equation is what? Governing differential equation. So from your mathematics background, if you have a governing differential equation and this is a domain, this is valid in which region? Or how can you solve a differential equation? If I ask you d square y plus dx square plus 2x is equal to 0, is this sufficient to solve the entire equation? Or some more information is required?
Initial conditions have to be given for the
So you require what?
initial
Boundary
Boundary
conditions.
conditions.
Yes.
Boundary conditions. So the beauty is, although Navier-Stokes equation are only set of equations, if you have an aerofoil, you have a sphere, flow is flowing past these, or you have a flow in a pipe, will Navier-Stokes equation change for these three or not?
No sir.
So what will change? But you get different velocity field in all the
Boundary
cases.
condition sir.
Only the boundary condition is making the change in the field. So what does that mean? External flows like this or internal flows like this, these are just providing what? Boundary conditions to
Navier-Stokes.
Navier-Stokes equation. It is as simple as that. So if you think every concept in this fashion, it will boil down to a simple solving a differential equation, nothing more than that. So if you are solving for an aerofoil, you are solving for a bluff body like say a square, a circle, you are solving for flow in a complicated pipeline which is having circular cross section or having rectangular cross section or any cross section, then you will be applying Navier-Stokes equation only. The results will be different only because you have different boundary conditions, nothing more than that. That is why it is not far from truth that if you have understood Navier-Stokes equation, it is just a mathematical manipulation afterwards that all the other equations boil down to solving this differential equation only, nothing more than that. Is that clear?
Yes sir.
So Navier-Stokes equation does not have solution for all geometries, and that is why we need to devise certain approximations to this equation. And rest of the fluid mechanics is just the study of those approximations, nothing more than that. So Navier-Stokes equation is, that's why called the cornerstone of fluid mechanics, because if you have understood this equation, other equations you can formulate by treating or approximating certain terms to zero, and you will get that equation. For instance, Poiseuille equation, Couette equation, Euler equation, Darcy equation, any equation you name. So I will break for today and we will continue with this